Today I'd like to talk about theoretical and percent yield. This is where we start to use a whole bunch of ratios that we talked about earlier in one of the first videos on stoichiometry, and we start looping them back in with the balanced chemical equations when we balance them, which we learned about earlier. And this is where we actually start getting into the interesting parts of chemistry, in which we can actually predict the results of a chemical reaction. So what those results are, what our predicted results are called our theoretical yield. And our percent yield, essentially how much of our theoretical yield did we actually produce. A low percent, or a high percent yield means that you did the experiment very well. A low percent yield, which is the opposite of percent error, is essentially you do not want a low percent yield, because if you have a low percent yield, that means you did not produce anywhere relatively close to your theoretical yield. Percent error, by the way, is just a way of measuring how badly did you mess up. If you have a high percent error, then you messed up then something went wrong in your experiment. But if you have a low percent error, then you did your experiment very well. So that's just a little bit on percent error. However, over here we're going to be talking about percent and theoretical yield. So I have this problem here. For this problem, we're going to be using this balanced chemical equation over here. Two hydrogen atoms react with 2 moles of hydrogen react with 1 mole of oxygen to produce 2 moles of water. That's all. You can also read this as 2 atoms of hydrogen react with 2 molecules of hydrogen react with 1 molecule of oxygen to produce 2 molecules of water. So then I have this question: if 15 grams of hydrogen atoms react with 35 grams of oxygen atoms, what is the amount in grams of water produced? So if we take this, and we have to first find the limiting reactant. So we have to take grams of hydrogen and convert it essentially to grams of oxygen. So let's start by doing that here. So we're going to convert 15.0 grams of hydrogen to grams of oxygen. This is the preferred method, because if you use this method, then you don't have to do multiple calculations. However, the other method is to simply take both of the reactants straight to the product and compare. So you would convert grams of H2O into grams of water and see which reactant produces the least, and then use that one. However, this way you only have to do one calculation. So if I start with 15.0 grams of hydrogen on this side here, and we take grams of hydrogen to the moles of hydrogen, and I'm going to take moles of hydrogen to moles of oxygen, and then lastly moles of oxygen to grams of oxygen. So we can fill these in with 1, and 2, and 1 here. Then we know that 2.016 grams of hydrogen are 1 mole of hydrogen, and that approximately 32 grams of oxygen are 1 mole of oxygen. So then we can start crossing things out. So if I cross grams of hydrogen, moles of hydrogen and moles of hydrogen, moles of oxygen and moles of oxygen, we are left with grams of oxygen. So then I just need to multiply this out. So we'll get our calculators out at this point, and we'll multiply 15.0 times 32, and we'll divide that by 4.032, which is basically 2.016 times 2, and the answer that we get is 119.046. 119.0476. So we took that, and that's how many grams of oxygen that we need. Grams of oxygen needed. And that quantity is greater than 35.0 oops, Okay, I'm going to put the needed here in parentheses. So we have 119.0476, which we need to round to sig figs, by the way. But I'm going to leave it like that for a minute here. If we were to round this to sig figs, we would just take out this 0.476 and we just leave it at 119, because remember, we have 3 significant digits and the rest are all conversion factors. The molar mass is a conversion factor, the mole ratio is a conversion factor, so that just leaves us with that'll leave us with 3 significant figures, which we get from the problem. That's the general principle. If you have significant digits, they're usually given to you in the problem. So 119 grams of oxygen, which is the amount of oxygen that we need, is less than the 35 grams of oxygen that are available. Is a less than, so that makes it that oxygen is the limiting reactant. So now that we know that oxygen is the limiting reactant, we can get on to the problem. We can now take the 35.0 grams of oxygen that we have, and we can now convert grams of oxygen into moles of oxygen into moles of water, and last thing is moles of water into grams of water. So we can fill 1, 1, 2. Refer back to our chemical equation to verify that. Go back to our chemical equation. We see that we need 1 mole of oxygen to react with to form 2 moles of water. So we can put a 1 there, and then the molar mass of water is 18.016. 18.016, and the molar mass of oxygen, as we saw previously, was 32. And so now if we take 35, now we just need to multiply this out. So we'll take out our calculators again. 35 times 2 times 18.016 divided by 32 gives us 39.414, because remember we have our significant digits here. Speaking of which, I need to cancel these out so that we don't get confused on our units here. So our significant figures, we have 3 significant digits, and our unit here is going to be grams of water. So we're going to create 39.4 grams of water. Now there's a part B to this problem. We're going to say that for part B, that 28.3 grams of water were produced. What is the percent yield? Well, we know that percent yield is equal to the actual yield divided by the theoretical yield divided by the theoretical yield multiplied by 100. So if we look at the actual yield, which we actually got, the amount that we actually got was 28.3 grams of water. So we take 28.3 grams of water, and we divide that by how much we expected we were going to get, which is 39.4 grams of water, and we're going to multiply that by 100. Conveniently, the grams of water cancel out, and we are left with 28.3 divided by 39.4. When we multiply that by 100, we see that we got 71.8%. Again, significant digits. We have 3 significant figures. 8%. That's our percent yield. So, essentially, percent yield is the only new formula here to calculate. What the theoretical yield is, this is the only new formula that we discovered. What we found when we decomposed the theoretical yield is that the theoretical yield is simply just a combination of all of the existing formulas that we knew. If you at this time would like for you to go back and revisit our limiting and excess reactant video, because that's a very important part, and this is actually the most complex part of the problem. When we get over here, it's a matter of using the conversion factors, which you already know, to convert the grams of the limiting reactant into the grams or desired unit of the product. So we could even further say that we could convert this into atoms, so there would be different conversion factors. So also go back and view our conversion factor video. And if you still have questions about it, then you can check out our group chat here, which we will be addressing every meeting. We will be addressing this, and then after some time, take a look back at these. This is a good way to essentially bring together all of the concepts of stoichiometry through theoretical and percent yield.